Well, thanks everybody for joining. Today is April 28th, and sort of a special presentation today for our seminar. We have our center's own director, Dr. Scott Bailey, who's going to be talking about some fun things, I think, about being in Alaska, very wee hours of the morning at very cold times. So without further ado, go ahead.
All right, cool. Thanks, Kevin, and thank all of you for giving me the chance to do this. I really appreciate it. You guys know me, I'm an informal speaker. I really hope there are questions. I really hope there's interactions and that we can talk throughout this. I hope I make you smile somewhere along the way. I promise I'm trying to. So let's be as interactive as we can, if possible. There's a long list of names on this slide. For a mission like this, to put it together, there's an awful lot that has to come together and work, and it takes an awful lot of people being committed to it and doing a great job. We've been very blessed with an awesome team, and I'm not going to go through all these names today. Some of them you're going to hear along the talk, but I really want to thank everybody who played any role, whatever that be, and there's a bunch of you. I want to especially thank my two closest colleagues, Bill and Justin. I won't be able to tell everything there is to tell about this project. There's been some ups that were pretty high up, and there's been some downs that were pretty darn low. But we three have weathered it all together, throughout. Like I said, I'll only hint at that. And so I just want to appreciate their partnership and the way we work together and the friendship and all that. Bill's been a friend and mentor and teacher to me for almost 30 years, since my early days as a graduate student. Justin's also a friend and colleague and a teacher and mentor of mine since he was a student almost 20 years ago now. And so I just want to thank you both for that and thank everybody involved. I'm not really going to talk much about the Aurora, but what we're going to talk about starts with the Aurora. Obviously, to all of us in this field, a beautiful phenomena. Our interest is in not just the glow of it and the physics of the Aurora itself, but where some of that energy goes. And one of the things it does is create a molecule, nitric oxide. A simple way to put it is the Aurora breaks up the really tight bond of molecular nitrogen, frees up an atomic nitrogen, which can react with O2 and form nitric oxide. There are many reasons to be interested in nitric oxide anywhere in the Earth. But one of the crucial ones is that if the nitric oxide can find its way down in the atmosphere to the ozone layer, it will catalytically destroy that ozone. And this is known to happen at some level, but we don't understand how much or how often. There have been lots of measurements of nitric oxide, but the place where this transport downward happens is the only place on Earth where there's time where the nitric oxide survives long enough for that transport to occur, and that's in the polar winter. The reason that's true is sunlight breaks up nitric oxide, destroys it, and so it's only in places where it's dark for a long period, days, where the nitric oxide can make it down to where it can really do some damage to the ozone, and that's the polar winter. What's interesting is we have a lot of difficulty measuring nitric oxide at night, so we don't know how much nitric oxide is really there in the polar winter. This is a figure from a mission someone's worked on called Snowy. And so as a function of latitude in the y-axis and time in the x-axis, you can see how much NO is here. And you look when you get up to high latitudes in the winter, you see lots of NO, but as soon as you get to the region where it's dark, we can't make the measurement anymore. The technique doesn't work there. The reason that's building up is, again, you're losing sunlight. The less sunlight, the more the nitric oxide can build up to. Just what does it build up to in here, in all of these polar winters? That's our question. Question's been around for a very long time. People have wanted to make this measurement long before I was even in this field. But what Bill and I decided to do and first proposed in 2006 was to use stellar occultation. So a star is essentially the light bulb, and then we measure the attenuation of the starlight through the atmosphere. And we do that as the rocket goes up and then down. And by getting a profile of that attenuation of the starlight at very particular wavelengths where nitric oxide absorbs, and it's a very narrow wavelength region. By looking at that attenuation, we can get a profile of the nitric oxide density. This was the idea. Like I said, we proposed it in 2006 and had our first flight in 2011. I want to say we actually are not the first ones to measure nitric oxide at night. There have been some, but all the measurements before us have some very significant limitation, like they rely on assumptions that are hard to back up, or they have really, really coarse altitude resolution to where they're smoothing out the profile to a degree that makes it hard to interpret something. What we add is a very direct method to measure nitric oxide that doesn't rely on any tough assumptions, and it can have very high altitude resolution. So this is our planned approach. We studied this extensively in the early days to figure out, how high we need the rocket to go to see the NO where it's created, which is about 100 kilometers and lower. The geometry we need, we realized that, okay, to make this work optimally, right, we want to go to an altitude like 260 kilometers, but have the altitude, have the rocket angle something like 100 degrees off zenith to look down at the star so that we can get a profile as the rocket goes up at the altitudes we're interested in. This geometry is crucial. If the star is too high, you look at altitudes that are too high and you're not interested in. Star is too low, it can go behind the Earth and you don't even see it at all. You need to launch when you have exactly the geometry you want, which is this, have the rocket at a particular altitude, and that's the one thing you can control is where the rocket goes, and then have the star in exactly the right place so that you're looking at the altitudes you want to look at. Really, that rocket altitude is it, right? There's no other, we can't like go up there and do like Star Wars and travel the rocket all over the place. It's got one profile. And so having the right geometry is crucial. And what that eventually translates into is launching at the right time so that the star is at the right height of the sky. And that's where Kevin mentioned the wee hours of the day. For our star and our mission to look at the altitudes we want, we have to launch near 4:40 a.m. I'm going through some detail to explain this because this is something all of us, but certainly me, sweat to a very large degree, is making sure we plan this mission out to launch at the right time to have the star in the right place. It's only like that for about half an hour launch window. And so getting it right is very important. And some of the students who've worked with me will tell you that very often, not always, but when a student starts to work with me, the first thing I have them do is do this calculation, right? Set up this geometry and tell me when I want to launch the rocket in order to see the altitudes we want to see. A lot of students did a great job on that. Some of them didn't really want to continue after that, but I'm grateful to all the ones who did it. We certainly got it right, but this is something that we pay a lot of attention to. Just to show you the geometry another way, we're going to launch the rocket out of Poker Flat, Alaska. NASA maintains a rocket range up there that's run by the University of Alaska. And so we're starting just north of Fairbanks in a region called Poker Flat. The rocket has to fly northward just because that's how the range is set up. They don't have, the people own property in different directions. You can't launch over a town or anything like that. So you're sort of forced to go this trajectory. But you can, of course, point the rocket in any direction you want. But we're interested in the polar night, so we want to look north. We picked a star that has the right UV characteristics, which is positioned in the north part of the sky. And then we time the rocket to be able to look in the right geometry we want. And so this is sort of how we do it. And this is the couple hundred kilometers that the rocket travels during the course of the flight, pointed at the star. This is the figure on the right is the same thing, looking a little smaller as that rocket trajectory again, and then the point. And now I put gray circles, the outer one to represent where the polar region is. So the rocket travels through the polar region, but it's always looking, right? The tangent point altitude where we're looking and making observations is always in the polar night the whole time and well into the polar night. This inner circle is a region that has not seen any sunlight for months when we get there. And so the NO has had time to build up to whatever concentration. And so the idea is to measure NO at a time when we expect it to be both high in density and low in altitude if our theory is correct in understanding of how nitric oxide should behave. Stars named Algenib, it's picked for its position in the sky and its UV characteristics. We want to launch near the end of January, again, so that we're looking at a region that's been in the darkness for a long time. So we sort of want to get right before the sun starts to show up again, and the geometry is like 4:40 a.m. The NASA guys really loved us for that. And just to show you again the zenith angle, this is how high the star is in the sky, at least from the rocket geometry, as a function of time. And what you see is, these are 50 minutes intervals. You see that over the course of a few hours, it comes up, gets close to exactly geometry 1, and then gets, then starts to set again. So we need to launch in this time period, which gives us something like a 40-minute window to get a geometry that'll work for us. And so the way we implemented that was to plan the rocket for the beginning of that window. And then when we got there, we did a hold for 20 minutes to get the absolute best geometry and then launch right in the center of it. The instrument that we use is a classic UV spectrograph. This was designed by Bill. In a rocket, you want a rugged system. In the UV, you're going to use as few optics as you can. So this is a simple spectrograph, although it's high spectral resolution, so it's large, this half meter focal length. It's fed by a telescope with an aperture, one mirror to collimate it, shine the light onto a grating, another mirror to collect that and then focus it onto a detector assembly. So fairly straightforward in terms of the instrument. And where we pay a lot of attention is to make sure this is focused and make sure it's going to stay focused upon launching. So all this has to be rigid and Helfersed out so that when you launch it at 18 Gs on a rocket, it's going to hold that focus and still work. But we fly a TV camera that I'm going to talk about in just a minute. Feeding that spectrograph is a telescope. This is something that Bill actually used in many previous flights, used to use it to study Mercury and Venus. But we adapted it for this mission. You can see the primary mirror in here. And then at the center, we place a star tracker. Here's a picture of the star tracker. So the star tracker can help us with the pointing of the rocket. And I'm going to talk about that in a little more detail. But with a Cassegrain design, you're using the outer parts of the mirror and then using the inner part to in this case, house a star tracker and then focus the light to go through the mirror, through an aperture in the mirror into the spectrograph. Here's what it looks like, a schematic of it put together. So we have up here or in the bottom in the telescope region, the rocket motor would go here and then fall off. There's a door mechanism that goes here that opens up once we are finished with the rocket motors and start to point the rocket. So a door mechanism points this at the star. That feeds the spectrograph, and you can see the length. The telescope is big, 22-inch diameter, 3-meter effective focal length. But there's a secondary mirror here, focuses the light into the spectrograph, and that's about 0.5 meter. And then we have one more section for the electronics. And you notice this rocket is larger than normal. Most Black Brant rockets, the typical NASA rocket, have an 18-inch diameter. We have 22. It's so we can hold that big mirror, and we want the big mirror so we can have lots of collecting area to get a lot of light from the star. We need as much light as we can. And then you see once you get away from the experiment, the rocket goes to its nominal diameter of 18 inches. And then all this put together, this is what we build, this is what we can take to NASA to integrate with their systems, a radio, a pointing system, battery pack, etc. This is what we built, and it came out at about 316 pounds. So that number is going to be important with something I'm going to show you in a few minutes. Now I want to talk for a minute about one of the hardest aspects of doing this measurement. So I told you we put a star tracker in the telescope, and a star tracker, these devices are incredible. You can point that star tracker in the sky, and it can tell you where you're pointed to within a few, probably arc seconds, certainly better than arc minute. And that's no problem. You can point it anywhere in the sky. It can look at the star pattern and figure that out. So from a technology perspective, it is very well known how to take a rocket like this and point it at any star we want. But we're not doing astronomy. We're using the star for a very specific purpose. And this is an image from the star tracker from our first flight in 2011, right? This is the star we were looking at that time. And you notice a couple of things. One, it's all dark down at the bottom. Well, that's because the Earth is partly in the field of view. We're looking at a star very near the Earth so we can study the atmosphere. You also notice the Aurora was active while we launched. So the Aurora is in the field of view of the star tracker. So both of these are aspects that could confuse the star tracker when it tried to use the pattern of stars to figure out where it was looking. More than that, this is Alaska. And even though this is there are all kinds of rules, you know, they don't let anybody fly out of the airport while we're doing a rocket launch for safety reasons. Alaska's, you know, a very independent-minded state. And so when we flew this the first time and we looked at the star tracker images afterwards, we saw that somebody wanted to watch the flight from their plane and flew right across the field of view of the star tracker. And you could just see the plane fly through. All these are reasons that a star tracker is not going to do, or not necessarily going to do, a good job while we're trying to make the measurement we want to make. And so the star tracker can get us an initial pointing. It's not something we can use throughout the flight. And this dictates a lot of how we plan and implement the mission, is knowing that we can't rely on this. And in fact, we actually don't use it for any closed loop control of the rocket, the star tracker. What we do is, remember I told you there's a TV camera in here. If the telescope is feeding a spectrograph, and of course, if everything is lined up, the telescope is pointing at the star, that starlight will go right in the entrance to the aperture of the spectrograph. If it's close, but not quite right, then the telescope light will be focused on the aperture of the spectrograph. And you could say, why don't we just make the aperture bigger? Well, that would bring the light in at an angle that wouldn't work for the spectrograph, right? We effectively would be looking at the wrong part of the spectrum if we did that. So we need an aperture with a fixed width in it. And if we're misaligned with the star, the light will go onto the aperture and not into the spectrograph. Well, what we can do, and this is a trick Bill has used, you know, many times before our flight, and astronomers in general have been using for decades, is you put the TV camera in here, a relay mirror, right? So TV camera looks at a mirror, goes through a lens to another mirror, so that it's looking at the aperture. And so real time during flight, we get as aligned as well as we can with an initial star that the star tracker can fix onto, confirm that we have our initial pointing right, and then we maneuver down to look at the star we're interested in. And then either the star goes right in the hole and the spectrograph is fed with light and we can make a measurement, or more likely, the light initially, because of the maneuver and the errors in the maneuver, shines onto the aperture. And then we have a very skilled person in Justin who looks at the TV camera image, looks for the image of the star, and then as necessary, corrects the pointing to force the light into the aperture. This is something we work on and we plan and try and think about a lot to make sure we're as ready as possible to do this measurement, because it all comes down to this. If you don't get the light into the spectrograph, there's no measurement worthwhile that's going to be made. So please stop me if I'm not making this clear. It's one of the important things we do to get prepared for this flight. Like I say, I'm not going to go through all the discussion of the low points we had, but in 2011, we tried this and it actually didn't work. And we had a really fluke issue with these are the relay mirrors that I told you about that go right here. And if you look really close, this has a layer of crud on it that I promise you was not there before we launched. It showed up during flight, some evaporation of some oil, probably from the rocket skin having not been cleaned well enough, or maybe some other things. When you go into vacuum, all that stuff evaporates and it's gonna consolidate onto the coldest surface typically. And the way we had our rocket set up, the initial evacuation was the air flowing this way to get out during flight. It cooled off this relay mirror. The small trace amounts of crud evaporated, but then collected onto the one cold surface. And so we got a layer of oil into this. And so when we went to look at the TV image during flight, we couldn't see a star. All we saw was defocused gray light. And so we lost the mission over that. But it's a survivable problem for the future is you evacuate the payload, right? Make sure it's under vacuum to begin with so you can pump out any stuff that would normally or would have the ability to condense onto that mirror. And so you just avoid it totally. And so that's what we did for future flights. And it took a little while, but we were given permission for a second flight in 2017, and we had a second problem where there was electronics failure. So a second major heartbreak. But thankfully we were funded to do this one more time. And the reason we got that funding is because I believe, NASA understands the importance of this mission. And there's a lot of backing from the scientific community. And I think we showed them we could do it. This is just a hard measurement to do. And so we got that permission. That was the flight in 2020. I want to show you a little bit about what it's like to test. So here is the TV camera image where we took the telescope outside. You can all remember this building. Space at VT used to be in this up until September. We just wheeled it outside the lab out into the parking lot, pointed it at a star, and got this image inside the TV camera. This does a couple things. One, it shows us what a star is going to look like when we're in flight. The only way you really know what it's going to look like is to go out there and shine a star through it. You can do all kinds of simulations in the lab, but what you want to do is pick out a star that's about as bright as what you're going to look at in flight, go out and point at it, and then look at that and say, okay, this is what I'm going to see in flight where I have a very short time to do the alignments. I know what this is going to be able to look like. I'll be able to find it when the time comes during flight. The other thing it does is it verifies we're in focus. That the fact that this is a dot means the optical system is in focus. We do a lot of work in the lab to make sure it's in focus, but life is complicated. There's ways to fool yourself in that situation. You can't argue with Mother Nature, right? That star is a star source. It's just like what you're going to look like in flight. If it's focused here in this situation, it's going to be focused in flight too. And so this gave us a lot of confidence. That's why we went out there and did it. I just want to spend a second talking about the actual action of it, because when I started talking to Bill and Justin and we talk about taking a 300-pound telescope outside, on a cart at night to look at a star, and it's not like we have some big fancy electronic gimbal that we can mount the star in like a fancy telescope and go out and point, right? I mean, you see the crane we're using, and the telescope starts mounted to just a cart with wheels. I start thinking about that, and I just think, wow, what a pain that's going to be. What a phenomenal pain that's going to be to do that. But take a look at the faces, right? Does that look like a group who's suffering, who was really doing something hard? Of course, this picture was after we finished, but these smiles reflect what it's like. We talked about it, we planned a lot. We still had to do some improvisation when we got out there, but I don't know, you guys remember a couple hours or something was all this?
I think you're forgetting that we had to go 2 nights.
Oh, I did forget that. Okay. Oh, yeah.
These must have been the smiles after the second night.
Okay. That's what my mind does. It gets rid of some of the more difficult parts. So it took 2 tries. And I, to be honest, don't remember what lessons we learned on the first night, but when we took it out on the second one, it was pretty much smooth sailing. It took some brute force work with that telescope to get it aligned and held there long enough to get pictures like this. But you guys pulled it off real well. And I remember having fun. And I'm pretty sure, yeah, I'm pretty sure this picture was taken before I told everybody there was a freezer full of ice cream down the hall. And I just want to make that point, to be successful in life, you got to work hard, but the really important thing is to work with good people. And that is something we got right throughout this entire project. And I'll probably say that a couple times, but this joy is real. And the experience of doing what I consider a difficult test, difficult setup and everything. I thought it was a lot of fun. Like Justin is pointing out, I totally forgot the problems we had. I want to stick on that theme a little bit more. This is us putting the payload together just before we took it off to tests with the NASA group. And want to mention Weston Allen, who's on our team. Weston's a mechanical engineer. He did a lot of the mechanical design on the payload. And so he's crucial to having set up, you know, how this all comes together mechanically. There were others, and I might point them out. But Weston was crucial to that. But one of the main reasons I want him there when we put the payload together is he's very meticulous. He and careful and very experienced. And he will look at every one of the screws on this payload, and there's 200 or 300, and make sure it's clean enough, make sure it's the right type for the way it's being used, make sure that it's torqued at exactly the right value. He has the patience to do that well and the experience to know it's done well. And when you fly things in space, you know, one, there's no second chance. It goes up there and what happens, happens, right? It has to be reliable. And there are only a few people who have the experience base, you know, that when they say this is ready, you really know that it truly is ready. Somebody tells me something's ready to fly, I ask a lot of questions because that's all I have, is to ask, did you think of this? Did you check this? You know, what you really need are people who've been down the road many times, like Bill is optically, you know, Weston is mechanically. And, you know, he will check everything. You know, he's going to be careful and is ready to fly. But the real point I want to make when I show you this slide is I'm the #1 fan of working with students. I think students do great work. You know, their contribution to this project is immense. Their contribution to every project they're on is tremendous. Plus, they make it way more fun. But the one thing a student can have is that experience base that Weston has. Students bring enthusiasm, the energy, and all kinds of capability, right? But the best thing we can do is when we pair our students up with people who have this kind of experience base. And I'm really proud of anything I'm proud of in any of my work is that we do stuff like this, right? Because then students really learn some of the lessons learned that Weston, right, learned, you know, through hard fought experiences, right? Samia picks up some of that. And I do want to be clear, who's really doing the work here, right? This is Weston helping, Samia putting something together. Here's the two of them again over here, right? With Samia working in a position I don't think Weston could easily get into. Certainly I could not get into. And I have pictures of Samia on top of the payload on every side, you know, right? She had an access to things that was way better than any of us could have done. We might have had to lift this payload up to be able to access certain parts we wanted or roll it around. It would have taken much longer if we did it. But here, I think we're providing a student with a great experience and mentorship, and they genuinely make it better. A lot of things come easier to students than come to some of us with gray beards, and the enthusiasm is just off the charts. Moments like this were just a tremendous amount of fun, and I think made the project much better because of it. Couple of the good moments. This actually was one of the hardest days on the project, although you can see it ended well. One of those Sundays, just a couple days before we were leaving for NASA, everything stops working. We can't figure out the problem, right? Things are intermittent, coming and going. We didn't know what. And we were sitting there and it was kind of a downer. I think we were getting to where we thought we might have to have a delay. And this song comes on, Back in Black by AC/DC. And yes, I admit to having a kind of a metalhead streak a little bit. But as it came on, and Brett can correct me if I tell this kind of wrong, this is Brett Fleming, key to our software and electronics. When that song came on, I turned around and said, you know, this all kind of sucks, but I do have to say, I really respect anybody who works to AC/DC music, right? That does make the project much better. And no kidding, while that song was still on, he found a pin in the electronics that was not connecting just right. And as soon as he plugged it in properly, or gave it what was a temporary fix at the time, everything started working. and all during that song. And so we decided Back in Black had to be our theme song. I actually have more Back in Black stories, but I'll stop at that one. And this cheer you see here is Brett having solved the problem and some kind of attempt to dance to Back in Black. Won't dwell on this side, but just wanted to say, I know who put the dents in the payload. Most NASA projects, you're not allowed to use a hammer onto the experiment, but we do, and we do it to great effect. And so, proud group of people with a working payload, fully tested, ready to head out to NASA, first to be integrated with the NASA sections, which is done at Wallops Flight Facility here in Virginia. So this is before we go up to Alaska for the flight. But there you see a lot of tired smiles from what had been a long haul getting this ready. And so here's some pictures from us testing at NASA. You do some outdoor testing actually, so that we can test out the GPS system and the radio system. There's a can't quite get the name of it out, iridium system in there that we want to make sure they work, and so they need access to the sky to test those. Most of it is done inside. One of the things we do is a vibration test, and also test to find the mass properties. So the rocket gets mounted in this way, and we do some spin testing of it, but also some vibration testing of it. These are all really wild things to watch. Before and after we do any test like that, we test the alignment. We need to make sure that the star tracker, which is right here, is aligned to our experiment in a way that is understood. And so this is us in the lab. You can see our TV system here with the looking through those relay mirrors. And what you can't see over here is a light source meant to imitate the star. And so we're lining up on that. And then we're going to turn around and line up onto the instrument sections. And so we spend a lot of time making sure we understand that alignment. And we always do it twice, before and after we vibrate it, because you need to know that when you launch it, that alignment does not go away. So we probably spend 2 full days just doing these alignments, or close to that, and making sure it's okay and making sure it's understood. I say we loosely. You can see how hard I work at it. It's Justin and Bill, and in this case, Brett, that really put a lot into that. And then once we finished the testing at Wallops Flight Facility, we head up to Alaska and get ready for launch. We launched on January 27th this past time. And so that meant we traveled, I believe, on New Year's Day or the day after. In past flights, we had left even earlier than that, but I think I flew on New Year's Day or one day later. And so we're there almost a month getting this ready and then doing the launch. So this is us after we've done a lot of testing, got the rocket onto the rail launcher. So this rail launcher can lay flat, and then we lift the rocket onto it. That's done with inside a building. This cover can be wheeled over top of everything, although not when the launcher is elevated. We move it away before that. So we attach it in a sort of warm area. The air out here on this day was probably -30 or something like that. And then when we launch, we just wheel this away and then raise this and point it. You notice you don't actually see the rocket. The temperature is cold, right? This is -30 or something like that day. We've seen -50 and less during our trips to Alaska. So you don't want the rocket freezing before flight. So as soon as they put it onto the launcher, they immediately encase it in styrofoam entirely, right? You can see even the fins on the motors are encased in styrofoam. Just a bunch of sheets of styrofoam, a lot of toothpicks to hold it together initially, and then they use some glue. And then when they launch, this is still there. It just all kind of explodes as part of the launch process. But you don't actually get to see the rocket fully assembled except for a few minutes. And they don't actually let us around for a lot of that because the motors, for safety reasons. But this is how the rocket looks when it's assembled. When we're there, we just see it encased in styrofoam. This is the setup that Justin uses when he's doing the pointing. So this is the TV system you saw here with our circle that shows where the aperture into the spectrograph is. So during flight, if we're misaligned, you would see the image of our star. And Justin could use that and say, okay, I need to go this many degrees in this direction. And he could program in that command and move the star in the hole. We, as you know, had a time where we did this and it didn't work because the mirror got dirty. So Justin has been kind of ingenious in years since then. So we also have the star tracker image. We're not using it to control the maneuvers, but we can still look at what the image sees. And so he can mark the aperture of the spectrograph on there and try and use that. It's way coarser than our instrument. So he can kind of use the star tracker, and I'm probably wrong. That's not the aperture of the instrument. That's the outer circle, right? But he can use that as some information to get the star in. And then something that he devised, he takes that image and feeds it into another system and then blows it up so that, whereas here we can barely see the part that's the instrument because the field of view of the star tracker is so large. He sets it up so we can see better where our star is, more like this, so that when he calculates his maneuver, we have two pieces of information that are pretty good, one from the star tracker, one from our TV camera. But I like to show this for one reason. You can see the official NASA labeling right on all this stuff. This is rocket work. If duct tape solves the problem, then you fly the duct tape. And here, this is just us, modifying the screens to make them work for us. There's an even better story about this, and this is one of the things, a story I love to tell. This is a picture from the first launch in 2011, and here is a system Justin used, right? So he's using our TV camera to figure out what maneuver he needs to make. This is the system he uses to actually make the maneuver, and you can imagine he takes some crosshairs, moves them to the point where he wants to put the star image, and then presses a button, and then it moves over. It's kind of like playing a computer game, right? And Justin hopefully has practiced a lot using that, right? The crosshairs can move it over. It's fairly straightforward, but you need to figure out ahead of time where you want it to go. And so that's where our TV camera image goes. And in 2011 flight, we were just using that, not using the star tracker image that he created in later flights. And when we got up to Alaska and started testing, we had a realization. We had done the work to make sure the star tracker was aligned with our instrument, but it wasn't until we got to Alaska and we realized that the images were rotated from one another and in fact inverted. So for instance, if you looked at one and decided you need to move the star up on the screen, on the other one, that might mean you need to move it left. And so it was going to be very easy to confuse yourself as to what maneuver you had to do, or when you did it, whether the right thing happened or not. And so, me and some others got into a panic. We got to change. We can't change the design of the rocket. It's up there. It's time to fly. So should we change the software? Should we invert the image, that's on this console? Should we do this? If you do that, then you got to test it. How do you know you did it right? How do you know you're not going to cause some other problem? And if we do, how would we figure that out? All these worries. Well, Justin, right, said, well, I can just flip the monitor over to handle that 90-degree issue. And instead of looking directly at the monitor, feed the monitor into a mirror, right? Have the mirror marked up for maneuvers I might want to do. And then I just look at the mirror, and then it'll be exactly like the star tracker image, right? The mirror does the inversion, the rotation of the monitor handles the 90 degrees. Problem solved. Total cost to the public, $5 for that mirror. I think in a million years, I never would have thought of that. But he solved the problem trivially and successfully. It's too bad that, we got the crud on the mirror. Otherwise, he would have really proven this out. But in my mind, and I think in the mind of a lot of other people during that flight, he was a hero for coming up with a really simple solution to a problem that made a lot of us pretty nervous. And that, by the way, is Justin in a number of circumstances. So getting ready for a flight, there's a few things you got to do. None of us on the team are superstitious in any way, least of all me. There's not a superstitious bone in my body. But I've learned over time that there's a few things you just got to do before you go fly. One of them is donuts. You don't show up at that launch area on launch night without donuts, and that's just a rule. I learned that lesson the hard way, and the story takes a couple minutes to explain, so I hope you ask me that at the end. I'm not going to tell it now, But it's one of my better stories is the why donuts are required, but I assure you they are totally required. You can't fly without these. And another one is dinner at the Chattanooga Lodge, which is the only game in town anywhere near the launch site in terms of eating or anything. It's a very Alaskan thing, bar and restaurant, very rustic. And you have to take $1 and hang it on the wall somewhere. I've flown 5 rockets out of Poker. I always forget where we put the $1. So this time, we took photographic evidence to know exactly where that $1 went. So if we ever go back, we can find our lucky $1. Certainly in this case, that $1 was lucky and it worked. So these are not my only traditions. There are a few, but these are 2 of the essential ones, right? You got to go to Chattanooga Lodge and definitely got to have donuts. And pink are by far the preferable donuts to have. Now, in every endeavor, right, there's always some things don't go exactly right. Most people will tell you working with me that I'm laid back. I don't boss people around too much. I don't think, right? I take things in stride. I don't have many rules, but I do have one rule. Can't be in the presence of nuts. There's no nuts involved in rocket launches. There's no nuts involved in space science when I'm around. There just cannot be any nuts. I can tear up even in the presence of somebody who ate a peanut butter sandwich in another room 15 minutes ago. I just don't like it. But for some reason, even though I'm very clear about the rules and post them, look what everybody brings to the launch room, right? I mean, I asked for one thing, right? And I can't even get that one thing. Everybody, even on launch night, literally something like an hour and a half before we launch, Brett Poche, in the presence of this sign, right, pulls out a peanut butter sandwich. I'm sitting there nervous, preparing for launch, and all of a sudden I smell this horrible thing and my eyes start, tearing up. I'm like, what's going on? Here's Justin, he knows exactly what's coming. And Brett, like, what did I do? You just can't have it. There can't be peanut butter. I forgave Brett, but I definitely made sure the peanut butter sandwich disappeared. Some other things, we posted some pictures to give us luck. It started with Neil Peart passing away while we were up there. And then we had other ideas of people we wanted to be there. I won't mention them all, but I do want to point out Jim Johnson, who passed away between the first and the last flights. But he was crucial to putting together the first rocket. And he's somebody I knew since my earliest days as a graduate student. He was also, or even more so, closer to Bill. But just a great guy and a huge help when we first built this payload, and somebody we missed tremendously and really wish could have been a part of the project. But we definitely had his picture there and we're thinking of him. My advisor, and also wanted to point out that Brett tried to go with the payload, but we caught him in time before and pulled him out of there. And then we launch. Here's one picture of the flight from a still camera up on top of the hill. Another with a longer exposure. This is Weston over here. And then with the longer exposure, you can see the first stage, and then there's about 4 seconds between the first stage and the second stage, and then it ignites, and then the rocket goes into the clouds. Awesome, beautiful sight. Every time I've gone up there to fly for a year before the launch, I tell myself, I'm gonna be professional this time. I'm not gonna be outside on the ice during launch. I'm gonna be inside the control room, ready for what happens, because everything happens so fast on a rocket. I don't wanna have to run in on the ice and go back in, right, and risk falling down and have an accident during flight. I've always gone in with that plan. I've dropped that plan every single time and ran outside to see the launch. There's nothing cooler than seeing these and hearing them and feeling it. And maybe not much scarier than running back in afterwards and trying to be really careful not to slip on the ice. Another picture of the launch. This was taken by a photographer who was out there some ways away, and you can again see the first stage and then the second stage. And here you can get some sense of there was a faint aurora going on, and you can see the some of the landscape, right? Again, this was January 27th, so lots of snow. It was beautiful. This, by the way, for those from Space at VT, is going to be our holiday card next year, already printed. The rocket lands about 200 miles north of the launch site. It's really hard to see. I don't know that you can see this by zoom. So here's what a spotter plane saw a day or two after the launch. You see the payload, it comes in on a parachute. The parachute is actually still, outward when it lands. So the wind dragged the payload. If you are really close, if you saw a good version of this picture, you could see that there's a path in the snow where the payload was dragged because of the parachute it's holding it, and it moved in the snow. Fascinating that a little Charlie Brown Christmas tree, the parachute got wound around that, and that's what stopped it and left it in place. It took about a month to get this back because they won't send people out to work on this. Usually you have to cut down trees, and there's all kinds of trouble getting a helicopter to it. For us, it was really easy this time. It landed in about as easy a place as you could imagine. But they still don't let people out there digging and doing all that work in temperatures less than -25. So it took a month till we got a temperature above -25 on a day where they could go out there. And so by the time they did get out there, there'd been enough snow, and the payload was partially buried. So they had to dig it all out and then get it attached to the helicopter and flew it back. Then it gets brought back to Poker Flat, where it was launched from. This actually, again, because it took a month, so it didn't come back till almost March 1st, 2020. And you guys all know what happened. Before we could get somebody up there to pack this up and ship it, the COVID restrictions hit. So we actually didn't see this payload again until September. And we got to test it just before we moved out of the Space at VT building. We got to do enough testing to make sure it still worked 100%. In fact, being out there in the snow kind of cleaned it off a little. It looked pristine and beautiful, just as well as when we first put it in the box 6 months earlier. So it's downstairs in Whittemore now in fully working condition. It didn't sustain any damage during the flight. Just to tell you a little bit about the flight. So T=0 is when we launch and the rocket takes off in altitude. So this curve is the altitude as a function of time. And you see, 100 seconds, 200 seconds. This is all fast, right? This is a 10-minute mission. You go up, you make your observation, it comes right back. The motors are going till a little before 100 seconds, right? So here's the part where it's accelerated and then the motors fall off. And then soon after that, around 100 seconds, is when we point the star tracker at the first star and then maneuver down to the star that we want to look at. And we start to get lined up. And you can see that all that happens in just about a minute and a half. And so the time Justin had, and Sashwati was a part of this, to get all that lined up and working is something like a minute or a little longer. It's really intense and really fast, and something we practice a huge number of times to make sure we get it right. And really, in a sense, this went off picture perfect when we did it. We didn't have any trouble lining up. Justin was so ready. But I do want to take a second and say one thing that happened. Shashwati was at the console, whereas Justin was working the pointing. Shashwati was working the overall control of the instrument, where we saw the data coming out and any commands we would have sent to that payload. And I mentioned that in 2017, we had an electronics failure. Well, as we got ready for this launch, we tried to think through every possible failure we could come across and how we would handle it. Even what if the computer we were using to send commands locked up and we had to replace it? We actually practiced replacing the whole computer and making sure we could do that in under 30 seconds or something like that. What would you do if the software hung up and we had to reboot it somehow? We practiced all of that stuff. And it turns out that as we got into the flight, after the motors had burned out, and just as we were about to start the alignment on the first star, the software that Sashwati was using to watch the data, monitor it, and to issue commands locked up. And there was a brief second there where I thought, holy crap, it's a repeat of 2017. But no, Sashwati calmly, we had practiced this. She shut the software down, then reloaded it, rebooted the whole thing, not the computer, but the software, got it up and running again. Total loss 20 seconds, no science lost. This was all while the star was being lined up. I'm not sure Justin even noticed it when it was happening. My heart skipped a beat for sure. Sachwati didn't lose a second making this happen, and we didn't lose anything. And like I mentioned with Sami, those kind of experiences to me are invaluable. That's a very high pressure situation. You don't get too many of those in your life, but she really came through for it. So this is what the flight is like. We spent some time looking above the atmosphere to get the star brightness right, and then some time looking at the altitudes we're interested in, and that's mostly while the rocket is coming down so that we get the actual rocket profile. And then eventually we have to close the door because air friction and the payload starting to heat up. This is what one of our images looks like. So this is essentially a spectrum, right? You're seeing an image of the slit as a function of wavelength. So x-axis is wavelength, y-axis is a spatial dimension. We really just sum up vertically on these images to get the actual spectrum. And this is just the same image showed a couple different ways. When we put it together and we ratio the observation altitudes to the altitudes where there's no nitric oxide and we're just looking at the star by itself, you get nice flat transmission. And then when you look at an altitude where there is nitric oxide absorbing, you see a dent. And I wouldn't say this was some simple analysis. It turned out to be harder than we thought, but like the solution to many problems, you put Justin on it and then you get an answer a couple weeks later. And this all came out fine. We have a profile, this nitric oxide in column density as a function of altitude. We were able to fit that with an analytic description of the number density of nitric oxide. So, we know that there was 3×10⁸, and we know the shape of the curve that we can describe with scale heights. Some of you have taken aeronomy, all right, know what I'm referring to. So we got a good measurement, one of the first direct measurement of nitric oxide in the polar night. I won't spend a whole lot of time talking through the comparison to some other observations, but I will say quickly, we made measurements with nitric oxide at extremely low solar activity as described by F-10.7 or AP, right? Nothing had been going on that winter, nothing significant in terms of activity. Yet these black lines are NO density, and these tall lines over here are what other measurements were made in sunlight, but only a few hundred kilometers away. And we measured 10 times as much NO in the polar winter as what they measured. And these are histograms of what other experiments have done over their whole mission. So the amount of NO we saw was huge compared to any other measurement, way more than other measurements made in sunlight just a short distance away, and also way lower in altitude. So the theory I talked about earlier that we expect in the polar night there to be a lot more nitric oxide and at a lower altitude is totally verified by this. And there's actually a whole lot more I could say about the meaning of this altitude and the transport process that got the NO there. So there's a ton we're learning, and we're only at the beginning stages of doing the science work with this instrument. But given the time, I'm going to stop there and hope there's some questions.
Well, yes, thank you very much. Yeah, any questions? Feel free for anybody to jump in here.
This is Elena Lind. Thank you, Scott, for such an interesting presentation. I have to say that for the first time, I actually understood what you're doing after 3 years being here. Two questions. One, have you tried differential optical absorption spectroscopy to analyze the data? Because you look like the approach you're taking will definitely benefit from this, because I'm doing similar work all the time, and I just, I'm looking at it, it's a perfect candidate. Is that what you applied, or did you just do the Beers ratio?
We just did the Beers ratio. So we have thought of that to see if that would help our signal to noise. And, we are on a side pursuing some ideas about a possible smaller instrument that might do this. We can't do this from the ground. I'm not sure I said that.
No, I'm talking about data analysis. I'm not talking about actually, you can give me the data, I can run it myself, and I can tell you, is it a good candidate from a signal? We measure, sub percent of the absorption. So it could be very good. So another question, how heavy your telescope spectrometer setup? I mean, again, as a person who looks at the sun all the time, like there are all these parallels that I can see where we can actually practice this maneuvering, I guess, like to some extent with the camera and everything from the ground, if you can put that system on some kind of 2-axis, tracker. And, to kind of add to it, like with the instruments I'm working, we do have a similar kind of setup where we're trying to track the sun from the boats. So like where there is waves constantly, you're all over the place. And of course, the signal from the sun is significantly higher, and again, I'm not talking about 215 nanometers, I'm talking maybe 315 nanometers. So there is a difference there.
What you're talking about is exactly what we do in our balloon project for our solar occultation experiments. So you should talk to Justin. He's put a lot of thought into pointing things like that. This one's 316 pounds, so we have a gimbal that can support it, but not a mechanized gimbal. The way we pulled this off was students holding the rocket and moving it around. Thank you, students.
Yeah, great accuracy. Thanks.
Yeah.
And I am not going to hug the time, but your system can be very beneficial to measure bromine monoxide at 35 kilometers if you would like to have a smaller instrument, and like we can combine the instrumentation to do that, because that would be also very interesting project.
Oh, absolutely. And in fact, in one satellite proposal version of this, Bill and I have thought about putting CO as a measurement on there. Eventually we went to CO2, but that would help us too scientifically.
Okay, yeah, thank you. Any other questions here for Dr. Bailey?
I scared you off from asking about the donuts by saying it wasn't a short story, but that is the better story.
Sure, I'll bite. Not a pun intended there. What's the story with the pink donuts? I guess why do they have to be pink?
Okay, well, I won't be offended if people leave, because this is a couple of minutes, but I do enjoy telling this story because it's very funny and you don't have to embellish it at all. And it starts with a few people that I've worked with in the past. Brian Rose was one of the technicians on our flights, the first two anyway. This is him during the 2011 flight with his Batman helmet. And this is him the first time we worked together in 1993 in White Sands, New Mexico, also with the Batman on the shirt. He's changed a little bit over the years, but I actually kind of look the same as back then. But he plays into this story, and it starts with Jeff Beebe, who some of you know from working here at Virginia Tech. He's retired now, but he was with us on the first flight in 2011. And a few days before the 2011 launch, we were in the Chattanooga Lodge, which is pictured here. And we were having a conversation, and the owner of the Chattanooga Lodge was part of this conversation, and probably Bill and some others. And I was saying, well, for this launch, I want it to be something people remember. I want everybody on the team who's there supporting it, to come away from this saying they want to work on, the next time we launch. I want them to be a part of this program again, right? It was so much fun, right? They came up, right after Christmas. They left their kids, during the holiday season. They'd been there a month. I wanted it to be special. And so the owner of the Chattanooga Lodge says, right, Scott, I got you covered, right? I know how you can do this. People don't know this about the Chattanooga Lodge, but we have the best egg rolls anywhere around. Now, of course, he has the only anything anywhere around. The nearest gas station is 35 miles across a snow-covered mountain pass. But he said he had some great egg rolls. And I thought, wow, that sounds good. That would be different. Nobody would expect egg rolls on, to be the snack on launch night. And I trusted him that they were as good as he said they were. And by the way, they were. So I said, okay, egg rolls for 40, right? We'll pick them up, 9 p.m. or something on launch night. So we go forward, launch night comes, and Jeff Beebe was there to help, and he volunteered to go pick up the egg rolls. And so I said, great, that's a big help. And I hand him $100 cash to go buy the egg rolls at the Chattanooga Lodge. He comes back an hour later to the launch room, and Jeff was one who never smiled. He always looked very serious. And he hands me the $100 back. And I said, why are you giving this back? Right? Is there change? What's going on? And he goes, there's no change. And then he handed me a receipt, and a receipt for the egg rolls for 40, $850, which he had put on his credit card. It never occurred to me to ask, what the Chattanooga Lodge was going to charge for those egg rolls. Egg rolls for 40, I assumed a couple bucks per person, but no, $850. And I suddenly owed Jeff Beebe $850, which, I guess I could afford, but I was very worried about it, and just panicked. But it was launch night. I got over that pretty quickly, although it was a huge pain to get that money paid. But this is not even the funny part. So we get ready to launch and we go forward, and then suddenly there's a scrub, right? They decide they're not going to launch tonight. They didn't say anything. Just all of a sudden there's an announcement a little while before launch. We're not launching. We'll try again tomorrow. So we didn't know what was going on. Bill and I get in the car. We're up at the telemetry section where you monitor the payload, not in the launch building, which is down a big hill and at the launch site. So we drive down the hill and we head to the launch site. And as we walk up to what's called the blockhouse where launch is done, Brian is walking out. Now, like I said, I've known Brian, almost 30 years, a long time. He's a legend in this type of work at Wallops. He's been a technician for so long. He's done hundreds of rockets. He knows all kinds of stuff. And he's one of these people that can be really, really tough. We've all seen him in fistfights. I've literally seen him in Alaska, rolling on the ground, hitting somebody. He's that kind of guy, but he's also very likable. He's one of those rare kind of people who can pull off, being so likable when he's so rough. And you have to remember, right, we've just scrubbed the launch, and these are people who left, soon after Christmas, during the holidays, to fly up here and do this. They left their kids, they left their families, and they've been away for a month. They want to go home. So scrubbing the launch and delay is one more day away from the family, one more day up there in some hotel eating the same food every day. So as Bill and I walk up to the blockhouse, Brian is coming out, and you could just see he's steaming. You could see it from a long way away that he was angry. I knew him. I knew he was angry. And when he spoke, and remember, I have no clue what's going on, he starts saying, "This is your fault. This is totally your fault. You did this." And I'm like, "What did I do? I don't even know what's going on. We're down here asking what's going on. We didn't do anything." And then he goes, "Nobody, but nobody would bring egg rolls to a rocket launch. That is not done. You cannot do that. That screwed up everything. I can't believe you did that." Right? And then he goes, "It's donuts. You bring donuts to a rocket launch, nothing else. Egg rolls don't work. You bring donuts. This is your fault." And so that's how I learned that you bring donuts. And I learned it from a guy with that personality. And so every flight since then, I've made sure there are donuts present. This story is a lot more fun to tell when everybody's not muted.
Yeah. No, I'm certainly chuckling through a good bit of it. That's could certainly see that. No. But yeah, very good. Any other questions that anybody's thought of here over the last little bit?
Did you get the egg rolls?
The egg rolls were great, by the way, and I'm glad you asked about the egg rolls. After that night, there was not one crumb of those egg rolls left. You couldn't find them anywhere. In fact, I don't really remember eating them. I'm not sure I even got one, but there was not a sign of them. But with the donuts, I brought donuts the next night, and it turns out we had to scrub 4 more times before we were done. And I brought donuts every night, a new 6 or 8 dozens worth of donuts. And by the time we actually did launch, every corner of every building where any of us worked, any of those 40 people, wherever anybody was working, the corners were filled with stale donuts stacked up on top of each other. But I made sure those donuts were there.
Yeah, you can see the first night or two, they're good, but after a while, it kind of gets old. So I had a question though. You mentioned kind of briefly about the next steps. Is there kind of any next steps with this to go ahead that are kind of, I guess at least, you know, or what are the next steps, I guess, going ahead with this?
Yeah, so there's two paths. One, you know, scientifically, you know, just showing, you know, where the nitric oxide is and that there's large abundances. But scientifically, you know, why is it there? The nitric oxide is not created at that altitude, it's created much higher. And so the transport mechanism and what's governing that, we have a bunch of ideas that we want to pursue. But then also, you know, this was a really low activity measurement. What happens when there's lots of solar activity? You know, how much higher does that go? And when there's more NO produced, you know, does it end up getting lower in the atmosphere? So we need more measurements. In fact, we need a bunch of measurements. And the feedback we've gotten from NASA is they kind of agree. There's some aspects of the planning they want us to work on. And so we're going to repropose with that included. But scientifically, there's a ton to do. And then I hope, and Bill and I have been working on this for a long time, I hope one day there's a satellite instrument to do this, because making this measurement all over the polar cap and all throughout the season would just be phenomenal and fascinating scientifically, important scientifically too.
Yeah, very good, very good. So I haven't seen a couple of people drop off, but just one last call for any questions there. Give a chance for somebody to reach their mute button. Okay. Well, thank you everybody for joining, and thank you, Dr. Bailey, for that wonderful presentation. A lot of good stories, and to see how, you know, a mission kind of progresses throughout the years. So thank you very much for sharing that with us.
Sure. All of you, I appreciate you listening. Thanks to everybody who was involved with this. You guys rock. It was an awesome experience, and it was hugely successful.
Yes, thank you. And then I think, speaking of too, for next week, we'll have our last seminar of the semester and for this academic year next Monday, May 5th at the same time, and by I think one of your grad students, Saswati. So looking forward to hearing from that, and watch emails about the information about what that'll be about. So thank you very much, everybody, for joining, and I'll hang out for a little bit.